Hello everyone. This video is about matrix vector products. This is another new operation that we are not used to performing with numbers, but we can do it with matrices and vectors. The way it works is as follows. Given a matrix M by N and a vector of size N, we can multiply them together in the following way. I should point out before we perform this multiplication that the crucial aspect of this is that there are as many columns in A as there are entries in the vector. And it reflects in this general form down here. You see that if I take every single column of A and I think of it as a vector, so my vector A1 will be the first column of this matrix, then I'll have others. I'll have my second column and so on up until the nth column up here. Then there needs to be as many of these as there are entries of my vector Vn. The reason why that's so important is that multiplying my matrix A by the vector V will be the same as taking a linear combination of the columns of A. By definition, this product is exactly as follows. I take my column A1 and I multiply it by the constant V1, and then I'll add V2 times the column A2, and then I'll add V3 times the column A3, and so on and so forth until I get to the last column rescaled by Vn. As I just said, the product of the matrix A with the vector V is a linear combination of the columns of A with coefficients, the entries of V. In particular, the output of this product is going to be a vector with M entries, because each one of these columns has M entries. Let's have a look at a few examples. What I want to do here is multiply this 3 by 2 matrix by a vector with 2 entries. By definition, that will be 5, which is the first entry of the vector, times the first column of the matrix, plus 0 times the second column of the matrix, 2, 4, and 6. Well, multiplying by 0 gives me the 0 vectors, so the end result of this will be 5, 15, 25. Let's have a look at another example here. Again, I want to take linear combinations of the columns of A, so that will be 1 times the first column, plus 0 times the second column, plus 2 times the third column. And if I add these together, I get 1, 7, plus twice the last vector is 6, 2. And the final answer will be 7, 9. There's one particular matrix that is important when we talk about products. It's called the identity matrix, and it is the matrix whose entries are ones exactly on its main diagonal. It's always a square matrix, so it will have ones on its main diagonals and 0 everywhere else. Here's a few examples. This is the identity of size 2, and this is the identity matrix of size 3. You see there's 0 everywhere except for on the diagonal. And an exercise that I urge you to check is if you take any vector of any size and you multiply it by the identity matrix, you get back the vector itself. When you check this, I encourage you to think back about the standard vectors and notice that every column in our matrix I is a standard vector. This is E2 all the way up to En. The last thing that I want to mention today are a few properties of matrix multiplication. Some of them will look familiar from other kinds of multiplication that we did before. What are the most important? Well, if I multiply a sum of 2 vectors, it's the same as multiplying each vectors and then adding them together. Matrix multiplication commutes with scalar multiplication. So if I multiply a multiple scalar, I can pull out the constant and multiply the vector. It is distributive. A plus b times a vector is the same as a times the vector plus b times the vector. Here's something a little interesting. If I multiply any matrix by the corresponding by a standard vector, what that does is to extract the corresponding column of the matrix. I encourage you to read the other properties, and we'll be working with them, but maybe I shouldn't comment further on them. I'll see you in the next video.